Chapter 7, Reactions in Aqueous Solutions. There's the table of contents for the chapter. Okay, so predicting whether a reaction will occur, there are 4 driving forces that favor chemical change. A chemical change is a chemical reaction. Chemical reactions do not happen just because. There has to be something behind them driving them, causing them to happen. And so what is causing reactions? Well, if something forms a solid, if you're going to mix it and it forms a solid, that's considered a driving force for a reaction. If water is formed, we'll learn about some reactions called neutralization reactions, where water is formed as one of the products. That's a driving force. If there is a transfer of electrons from one substance to another, that can drive the reaction. And if there's a formation of a gas, it's another driving force. So, well, that section was too short, so I'm going to lump it in with this one. So let's talk about these reactions in which a solid forms. So here we have an illustration of a potassium chromate solution being mixed with a barium nitrate solution. The potassium chromate solution has a yellow color, and yet it is still clear. You can see through it. It's just got a color to it. And the barium nitrate solution looks just like water. And so it's important to remember, especially in lab when we're dealing with things, that not everything that looks like water is water. Okay? Some of it's not good for you. So barium nitrate solution. When we mix these two solutions, we get this yellow cloudiness forming. Okay, it does look like a jellyfish. It's little tiny particles. The reason we can't see through it, see, this is yellow and that was yellow, but that's clear. We can see through it. This we can't see through it. It has kind of a milky quality. That's because there's little tiny solid particles and we can't see through solids. So there's a solid forming. The solid is called a precipitate. Question?
Would that be kind of the same thing as silicone that's kind of like almost like a liquid and then like hardens?
Is that the same thing as the silicone that's a liquid and then hardens? Like the kind of a glue kind of stuff they use? I am not exactly sure about that. A lot of things that are liquid, like, let's think about Elmer's glue. That hardens because the solvent evaporates. The water leaves it. And so that's why it evaporates. And that's why a lot of those glues have a very strong odor, is because they have some sort of an organic solvent that evaporates a lot more quickly than water does. And then what's left behind is a solid. And some of that is involving a chemical reaction, and some of it not so much. But whoops, I don't know how I did that. That's a different process, but a good question. So I think we've done this in lab at least once, where we mixed 2 clear liquids and we got something cloudy. That's formation of a solid. We call it a precipitate. In meteorology, they refer to precipitation as snow, rain, hail, stuff falling from the sky, right? And this looks a little bit like yellow snow falling, right? So it's precipitation. I know, yellow snow. I grew up in Minnesota. Yellow snow was, we all knew why that was yellow, and you avoid that. And it's not just little boys. So here's our observation, that we mix the potassium chromate and the barium nitrate and we get this solid. How can we figure out what the products of this reaction are? Is there one product? Are there 2 products? How can we figure this out? That's a question that we're going to come back to and answer. So to answer that, we need to think about, well, what happens when an ionic compound dissolves in water? There was a solution of, potassium chromate? What happens when you put solid potassium chromate in water? Well, ionic compounds separate into ions. So their ions separate and they move around independently of each other. And so you can kind of see that in this illustration down here. We've got the positive ions and the negative ions, and they move away from each other, and they move around. They're free to move. And we'll explain a little bit more why they do that later. So here's a term we have, strong electrolyte. A strong electrolyte is a substance that dissolves in water and produces separated ions. The reason it's called an electrolyte is because it will conduct electricity. So here we have an apparatus with a battery and a light bulb, and the wires are not touching each other. If they were touching each other, the light bulb would go on. But they're attached to these electrodes that are immersed in a beaker of pure water. Pure water doesn't conduct electricity very well at all. It'll conduct lightning, but lightning can go through pretty much anything it wants to. But water doesn't conduct electricity. If we throw some salt in that water, just some regular table salt, the light bulb goes on, like you threw a switch. Because the salt dissolves into separate ions, these ions are able to carry the charge. Electricity is a flow of electrons, and the electrons need to flow in a continuous circuit in order to go through the light bulb. And so because we have ions in this solution, it allows the current to flow through the water. So that's a strong electrolyte. So when an ionic substance dissolves in water, it separates into ions. So then we can go back to our question here about this potassium chromate and barium nitrate and see, well, what happens? Well, here's the beaker with potassium chromate in it. The potassium ions separate from the chromate ions. Chromate, CrO4 2-, is a polyatomic ion, and that's like one of those bundle packs. It does not come apart. It stays together. It just separates from the potassium. So the chromate stays together. Over here we have barium nitrate. It does the same thing. The barium ions separate from the nitrate ions. There we go. In this formula, we have 1 barium and 2 nitrate ions. And so in this solution, we're going to have 1 barium ion for every 2 nitrate ions. The ratio's opposite over here. We have 2 potassiums for every chromate, because in this equation, we have 2 potassium ions and 1 chromate ion. Remember that ionic compounds have 2 ions, at least the ones we'll talk about in this class. Only 2. And so the potassium is 1, you cover that up. Everything else is the other ion. Don't try to separate the chromium and the oxygen. Okay? So we can write an equation showing this, where we've got 2 potassium ions and a chromate ion from this solution. And then we've got the barium ion and 2 nitrate ions from this solution. Those are the reactants the way they actually are. They're dissolved in water, so they're separated. And something's going to happen between these two that's going to make a solid. So here are the reactants listed as more of a chemical equation. It's going to form the products. That mixed solution, when we mix those two together, we have 4 different kinds of ions. We've got the potassium ion, and the chromium ion, and the barium ion, and the nitrate ion. Each substance had 2 ions, and we mix them all together, now we've got 4. So now we can just look at all the possibilities of what sort of compounds we could have. So here we're just listing the cations on the left vertically and the anions across the top horizontally, and we're looking at the various combinations. You could have potassium with nitrate, would be KNO3. You could have barium with nitrate, that's BaNO3 2. You can have potassium combined with chromate, or you could have barium combined with chromate. So these are the possible combinations. You can't have potassium and barium ions combining together because they both have positive charges. They're not going to get along. They're not attracted to each other. And you can't have nitrate and chromate forming a compound together because they're not attracted to each other. They have both negative charges. So these are the 4 possibilities of combinations between these ions. 2 of these are the reactants, aren't they? We've got the potassium chromate and barium nitrate are what we started with. So the potassium chromate was a yellow solution, but it was clear. That wasn't a solid in water. And the barium nitrate was a colorless clear solution. That's soluble in water. That wasn't a solid. So those 2 cannot be our products. The products must be the other two. So we're deciding which one is most likely to be that yellow solid. Well, potassium chromate and barium nitrate were both reactants, so we're pretty sure those are not the yellow solid. So the possible combinations are potassium nitrate and barium chromate. Now, it's listing white solid and yellow solid. Is there any way that you could know that at this point? No. But you could go look it up. And so, if we were really trying to figure this out, because, I know the answer. I've been through the slides before, if nothing else, right? You can go look these up, or you could find them on the stockroom shelf and look at them and see, oh, well, potassium nitrate, that's not yellow. That's a white solid. So that can't be the product. You find barium chromate, oh, that's a yellow solid. That looks a lot like this stuff in my beaker. It must be that. Okay, so this is one way that you could figure out what the products of a reaction are. So more illustrations. So here's our mixture. We've got all these ions mixing together. And we talked about what the possible products were, and we decided that it was barium chromate because that was the yellow one, and potassium nitrate wasn't yellow, so that couldn't be the solid. Did we see a white solid form? No, there was just the yellow solid. The potassium and the nitrate ions are going to stay in solution. So when we write this reaction, these were aqueous, meaning they were dissolved in water. And here we write the formula for barium chromate, and we put S because it's a solid. And the potassium nitrate remains in solution. So how do we know if the potassium nitrate is going to precipitate or stay in solution? We need to look at the solubility rules. I will not make you memorize this table. I will give it to you on an exam, but you need to know how to use the table. These are general rules. As with anything that's general, there are exceptions. And we do these in order. So, because occasionally you'll have two of these rules that appear to conflict, and so the one that comes first is more important. Most nitrate salts are soluble. Most salts of potassium, sodium, and ammonium are soluble. Most chloride salts are soluble, except, okay? So chloride salts are soluble except sodium chloride, lead chloride, and mercury chloride. Sulfate salts are soluble except for these three. Most hydroxide compounds are only slightly soluble. And then there's a little footnote. The terms insoluble and slightly soluble really mean the same thing. Such a tiny amount dissolves that it is not possible to detect with the naked eye. So when something is soluble, like table salt, if you pour a teaspoon of table salt into a glass of water and stir it, it all dissolves. And you can see, oh, yeah, that dissolves. With something that's slightly soluble, you can put the teaspoon in there and you stir it around, and then you look at what's left in the bottom and you're like, doesn't look like any dissolved. Now actually a little bit did, but not much. You can't tell. It's not like half of it's gone or something. So there's there's a continuum here. It's not all or nothing. There are some things that are slightly soluble, but for our purposes, if it's slightly soluble, we're going to call it insoluble, because it only dissolves a little bit. So hydroxide compounds are only slightly soluble, but there's exceptions. The sodium hydroxide, potassium hydroxide are soluble. Okay, and that goes up with here, most salts of sodium and potassium are soluble. Barium hydroxide and calcium hydroxide are only moderately soluble, so they're like kind of halfway. And then the sulfides, carbonates, phosphates are only slightly soluble. So when we say a soluble solid, it's hard to say, soluble solid, we mean that it dissolves readily in water. Insoluble or slightly soluble means that the amount that dissolves is undetectable with your naked eye. A little bit may dissolve, but you can't really tell. And then we use this term salt. When you think of salt, you think of table salt, sodium chloride that you sprinkle on your food. In chemistry, salt means any ionic compound. So salt is a salt, but potassium nitrate is also a salt, and barium chromate is also a salt, and sodium cyanide is a salt. And that's not something you would want to sprinkle on your food, unless you're a spy and you're trying to kill yourself. That might be good then, but
With moderately soluble, would that be insoluble or?
moderately soluble, I think we'll end up calling that insoluble as well. Yeah, we'll approach those as we get there. This is another table that your book uses. I like the other one better, but if you like this one better, that's fine. So without going through all that stuff we just went through with the barium nitrate and the potassium chromate, how can we predict what's going to precipitate when we have two ionic solutions mixing? The first thing we do is we write the reactants as they actually exist before any reaction occurs. And remember that those ions separate. If it dissolves in water, it's going to separate into ions. So we're going to write the individual ions. Then consider the various solids that could form. And what this amounts to is swapping partners. Okay? Exchange the anions. So here I get into one of my dumb analogies. So I've told you that the metals are like masculine, they're the men, and the nonmetals or the anions would be the females. So you have two couples going to a dance, okay, or a party. So you've got the guy and the girl, and there's a positive and a negative, and then you've got the guy and the girl, positive and negative. And so what happens at the party is that they end up swapping partners. Okay? So that's what we're talking about here. You just switch the anions. Then you need to use the solubility rules to decide if a solid forms. And if so, then you can predict the identity of the solid. So what you do is you swap the partners, and then you look in the solubility rules and you see, are any of those insoluble? Well, if something is only slightly soluble, or if it's moderately soluble, some of it will probably precipitate out, and so then we'll say it does form a solid. And so in the analogy, what that is, these were just casual dating couples, and they went to the party, and they're like, you're not so appealing to me anymore, and you switch, you're like, I like this other guy. And the solubility rules are telling you which ones are going to be so attractive that they're actually going to go off by themselves. They're going to go out in the back porch and make out or something. They're not going to mingle anymore. The rest of the couples there, the rest of the people are mingling, but these two are so attracted to each other, they're just like going to be together all the time. Okay? You've probably seen that happen. It's very, very strange. And disturbing, yes. And I told you it was a really stupid analogy, but you'll remember it. Okay, so here's a concept check. I can't talk today. Which of the following ions form compounds with lead-2 that are generally soluble in water? So how do we figure out which of these compounds are soluble or insoluble? We have to look at the table. So lead-2 with sulfide. What does it say about sulfide? It says it's only slightly soluble. I have to pull up my table here because I don't want to flip back and forth. So, chapter 7. So it says, rule number 6, most sulfide salts are only slightly soluble. So letter A then is not soluble, right? How about lead with chloride? Well, we start at the top, we look, rule number 3, most chloride salts are soluble. Notable exceptions are lead-2 chloride. Okay, so that one's also insoluble. How about nitrate? Oh, rule number 1, most nitrate salts are soluble. Doesn't give any exceptions. So there we have one that's soluble, this guy. Didn't mean to use that color. Let's use this color. Yep, and I circled the wrong thing. It's just batting 1,000. Sulfate. Okay, blah, 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 blah. Rule number 4. Most sulfate salts are soluble. Notable exceptions are PbSO4. So that one's insoluble. How about a compound between Pb2 plus and Na plus? Can you make a compound between Pb2 plus and Na plus? No. That was a trick question. So this is the only one that's going to form a compound that's going to be soluble. That one, nitrate. Lead nitrate soluble, lead sulfide, lead chloride, lead sulfate, not soluble. Sodium and lead together are not going to form a compound. Could you mix them together? Could you make an alloy? An alloy is a mixture of metals. Yeah, you probably could. Would it dissolve in water? No, it would not. But it also wouldn't contain ions. Another concept check. A sodium phosphate solution reacts with a lead 2 nitrate solution. What precipitate, if any, will form? Well, let's write some things down here. Sodium phosphate. Well, that's sodium and phosphate. And then we have lead nitrate, which we just looked at was soluble. Lead and nitrate. So what are the two possible products? Well, we have to switch partners. Guy and a girl, guy and a girl. Plus and minus, plus and minus. Okay? So the sodium and the nitrate, or the phosphate and the lead. Those are our two possibilities. Swapping partners. So then we look at each of these and we decide, is that soluble or not? So sodium and nitrate. Rule number 1, most nitrate salts are soluble. That one's soluble. Is that going to form a precipitate? No, it's going to stay dissolved in solution. What about lead and phosphate? Well, let's see. Down to rule 6. Most phosphate salts are only slightly soluble. So at least some of this is going to precipitate out, most of it actually. So that's going to form a precipitate. So it's going to be the lead and the phosphate. You see how I did that? You switch the partners and look and see how much do these guys like each other, basically. Because when you mix sodium, phosphate, lead 2, and nitrate, what's going to happen is that the lead 2 and the phosphate are going to go off on the porch, and they're not going to mingle anymore. They're going to precipitate out of the party. They're just going to sink to the bottom of the beaker and sit there, okay, being with each other. And the nitrate and the sodium are going to continue to mingle and have a good time. Is it possible to mix things like this and have no precipitate form? Yes, it is. If all the combinations are soluble, you're not going to get a precipitate. So let's look at this one. Here's a solution with all of these ions present. And if they're all allowed to react, and there's plenty of all of them, how many different solids will form? Well, we have to consider each of the combinations. This is not a simple problem. So we could write out all the combinations, or we could look at our rules and maybe figure it out that way. It says most nitrate salts are soluble. So nitrate's not going to precipitate with anything. So let's just cross him off. He's just, that's not going to precipitate. Does lead precipitate with things? He shows up as an exception to a few things. So we'll leave him in there. How about potassium? Rule number 2. Most salts of sodium, potassium, and ammonium are soluble. So potassium's not going to form any solids. And we've got silver. Silver shows up as an exception to solubility. We've got chloride. The chloride things are soluble except 2 of those. Sulfates are soluble except, and the phosphates are only slightly soluble. Okay, so we got rid of the ones that are always soluble. So let's look at lead. Lead 2. Is that going to form an insoluble compound with chloride? Yes. Rule number 3, most chlorides are soluble. Notable exceptions are silver chloride and lead chloride. So Pb and Cl minus is going to give us PbCl2. And while we're at it, what else did it mention in there? It mentioned silver chloride. We've got silver in here. So the silver and the chloride are going to also make a solid, AgCl. So we took care of the chloride. Those are the 2 possibilities for chloride with the lead and the silver, and they're both insoluble. Let's look at the sulfate. Most sulfate salts are soluble. Notable exceptions are barium sulfate, lead sulfate, and calcium sulfate. We've got lead there. So the lead with the sulfate, because it's asking you to write the formulas for them. It's saying to list them. And so you have to look at the charges to write the formulas. So PbSO4. What about silver sulfate? It says sulfates are soluble except, and it doesn't mention silver. So silver sulfate's soluble. We're not going to write that one down. Phosphates. Most phosphates are only slightly soluble. So we have 2 cations here, and so it's going to make an insoluble compound with each of those. So we've got Pb2+ with PO4 3-. It's not a 3 though. Never fails to amaze me how I can say one number and write a different number. There must be some significance to that. I'm sure it's not a good thing. +2 - 3. Let's do the crisscross thing. End up with Pb3 SO4 2. And then well, that is too big of an eraser. PO4. Thank you. And silver with phosphate is also insoluble. So that would be Ag3PO4. Now, for Chem 10, that's what I would consider a very hard problem. It's good to do in lecture, though, because it illustrates a lot of things. So how many different solids did we end up with? 5. And we have them listed there. There's lead 2 chloride, silver chloride, lead 2 sulfate, lead 2 phosphate, and sulfur phosphate.